6.6 is about related rates. Okay.
41.
Whoa, calm down with 41. Calm down with 41. 41, linear versus angular speed. Oh, okay. Yeah, we'll get there. Well, we can do 41 if you want. But let's look at some simpler ones first, and then work our way up to 41. So first, starting with something like number 1, 2, 4, something like that. Let's do just 2. No, 4. I like 4 better. Let's do 4A. Just as what we're doing. All right. So the problem says. In exercise 1.4, assume that x and y are both differentiable functions of t. Find the required values of dy, dx dt, and dy dt. It gives you the equation x squared plus y squared equals 25. And it tells you that to find dy dt when x equals 3 and y equals 4 and dx dt equals 8. That's part A. So it's asking to find dy dt when, and it gives you an x and a y value, x equals 3, y equals 4, and dx dt equals 8. So how do we go about figuring something like this out?
Do the implicit differentiation.
Yeah, so we're assuming, it tells us to assume that x and y are actually functions of time. They change as time changes. Okay? So if x is a function of time and y is a function of time, I can differentiate both sides with respect to t. So if you're trying to find dy dt, you have to get dy dt in there by taking the derivative with respect to t. So we'll take ddt on both sides. So now, the derivative of x squared with respect to time is equal to what?
2x.
So the derivative of x squared is 2x.
dx dt.
Right, but because we're taking the derivative with respect to time, you get an inside derivative, dx dt. Right, the derivative of x with respect to t is not 1, it's dx dt. Right, so whenever these don't agree, whenever the variable that you're deriving with respect to and the original variable in the equation don't agree, you get an extra factor. So then derivative of y squared, 2y dy dt, derivative of 25, 0, because there's no, it doesn't depend on time, it's constant. We want to find dy dt, and we have x, y, and dx dt. We have these three, put them in. This guy will be equal to 8. Y will be equal to 4. dy dt we don't know. X is equal to 3. And so I put in dx dt, I put in x, I wrote the 2 down again. I put in 4, and then I have to solve for dy dt. Yeah, so let's see here. 2 times 3 is 6, times 8 is 48. Plus 2 times 4 is 8. dy dt equals 0, so move the 48 over and then divide by 8. The algebra part. So if you divide by 8, dy dt is equal to 48, negative 48 over 8, which is negative 6. What does this mean? Okay, let me ask you this. What's this curve look like? Circle, right? Radius 5, right? X squared plus y squared equals 25 in the circle. Because this side is r squared, we know the radius is 5. So you have some radius 5 circle. Right, 1, 2, 3, 4, 5. when x is 3 and y is 4, basically what these calculations are going to tell you is if you're at the point 3, 4 on the circle, you imagine a little particle moving along this curve. If your x coordinate is changing at 8 units per second, right? This is a rate. So, right. So if your x coordinate is going 8 units per second in this direction, then to stay on the circle, your y coordinate has to go down 6 units per second. That's what this is telling you. If you go at any other rate in the y direction, you're going to fly off your circle. You're so sad. So very sad. Okie dokie. Let's look at 16. Surface area. All edges of a cube are expanding at a rate of 6 centimeters per second. How fast is the surface area changing when each edge is 2 centimeters and then again 10 centimeters? So part A and part B here. So all edges of a cube are expanding at a rate of 6 centimeters per second. How fast is the surface area changing when each edge is 2 centimeters? So let's see, we have a cube. Now, starting off here, all edges of the cube are expanding at a rate of 6 centimeters per second. So because this cube is expanding, these edges are changing lengths, okay? So I can't label them a fixed value. But I can label the edge length a variable, like x. So one thing you have to notice, what's the first thing you notice here? If this side length is x, what about this side length? X, y? Z. X, y, Z. This is x as well because it's a cube. And then the height is also x, right? A cube means all the side lengths are the same. So then the formula that we're going to need, well, I guess I can write down what I know. I want to know how fast surface area is expanding. Right? That's what it says. How fast is the surface area changing? So let me call that dA dt. This is how fast the surface area is changing. And they give me a couple of values. They want to know what dA dt is when x equals 2, and when dx dt is what? Let me read it again. All edges of a cube are expanding at 6 centimeters per second. How fast is the surface area changing when each edge is 2 centimeters? So what should dx dt be? 6 centimeters per second tells you that's a rate. So since the edges are expanding at 6 centimeters per second, you know that should dx dt. So what I'm going to have to give before I can find dA dt, the rate at which surface area is changing with respect to time, is a formula for surface area. I got my diagram, I got my knowns and my unknown, now I need my formula. What's the surface area mean, or what is it specifically here?
6 times x squared.
Yeah, so surface area is the amount of area covered on the surface of the cube here. So you have to take each face and find its area. Right, so for example, the front face here has an area of x times x squared. But you have 6 of those faces. You have a front face, you have a back face, you have a bottom face, you have a top face, and then you have the left and right face. So you can write it like that, and all your friends can laugh at you. Or you can rewrite it as 6x squared. This is my formula for the surface area of the cube. So in order to find the rate at which surface area is changing, to find dA dt when x is 2 and dx dt is 6, what do I have to do with this formula? Derivative with respect to time. Because I need to get a dA dt in there. So I derive both sides with respect to time. So A equals 6x squared. dt on both sides. So the derivative of A with respect to time is exactly what we're looking for. What happens over here?
12x?
Right, the derive just like normal, right, the 2 is going to come down to make it 12x, but because x is a function of time, what do you have to multiply by?
D over dt.
Right, these guys don't match, so you multiply by dx. And now I can find what I'm looking for, because I know x is 2 and dx is 6. So dA dt, when I plug things in, equals 12 times 2. Or 12 times 12, so on. 44. What's my units here? Centimeters squared per second. This is centimeters per second. So when you multiply them, you should get centimeters squared. Try 41. So number 41 from the homework, or from section 2.6. Tells you a patrol car is parked 50 feet from a long warehouse. The revolving light on top of the car turns at a rate of 30 revolutions per minute. How fast is the light beam moving along the wall when the beam makes angles of 30 degrees, 60 degrees, and 70 degrees with a perpendicular line from the wall? So they give you a picture here, which is also nice. Wall. Give you this police car with this flashing beam. This light here. It makes a beam like this. This guy is 50 feet from the wall. And label your angle. This is the angle theta. They call x, so let's use their. So how fast is the light beam moving along the wall when the beam makes angles of 30 degrees, 60 degrees, 70 degrees with a perpendicular line from the light to the wall? So what is it asking for? What's the theta dt?
8%, or the
How fast is the light beam moving along the wall? So this beam of light is hitting the wall and wants to know how fast it's moving as this guy spins. Right? As time goes on, this little light in here is going to spin, and it's going to make the beam of light is going to hit the wall further down. So it's asking how fast this point is moving as the beam of light spins. So since we call this distance x, it's asking how fast is x changing, how fast is x growing? So I would label that dx dt. So it's asking for dx dt, and it's giving us a couple of pieces of information. The revolving light on top of the car turns at a rate of 30 revolutions per minute. So what do you think 30 revolutions per minute is going to help me find? d theta dt. Now, personally, so d theta dt, I guess you could say, is equal to 30 revolutions per minute. But when you plug things in, you're never going to plug in revolutions, okay? You want, what do you think you want here instead?
2
Radians, right? I would much rather have radians.
4
So if you do 30 revolutions per minute, how many radians do you travel through?
65.
You multiply by 2 pi, right? Because 1 revolution is 2 pi. So if you times this by 2 pi, because there's 2 pi radians in a single revolution, you can get 60 pi radians per minute. That's a more useful unit, since everything we do with trig functions is in radians. I would convert revolutions to radians, because all my stuff that I've done with trig functions is in radians. And the other thing that we know is that, what else do we know? How fast is the light beam moving along the wall when the beam makes angles of theta equals 30 degrees, theta equals 60 degrees. So they give us theta. Again, I don't like degrees. So I'm going to convert this. What's 30 degrees in radians? Oh my gosh, yes. Yes. Now everything's in nice units. Radians per minute, radians. I can find dx dt, hopefully, if I come up with the right formula. What do you think the formula should be? What relates x and theta in this picture? What function? Yeah, if this is a right triangle, which is the assumption because it says that this is perpendicular, then you have opposite, which you want to know something about, and adjacent, which you know something about. So you can start right away by saying tan theta is equal to opposite over adjacent. So then, that's fine, but I want to know about dx dt. So I need to take the derivative of both sides with respect to t. It's the derivative of tangent.
Secant squared x. Or secant squared.
Secant squared or secant tangent?
Squared. No, secant squared.
Secant tangent, it's the secant.
Yeah, the derivative of secant is secant tangent. The derivative of tangent is secant squared. Okay, is this right?
Yeah.
What else do I need?
D.
Right, so the derivative of tangent of theta is secant squared theta, but then you have to do the times the derivative of theta. So times d theta dt equals, what happens on this side? Do I have to do quotient rule here? Yeah, so you want to hopefully start thinking of division by a constant just like multiplication by a constant. Right? X over 50, x over 50 is the same thing as 1/50th x. So if you want to do the derivative of this, you can do the derivative of this. So what's the derivative of 1/50th x? 1/50th. But if I'm doing the derivative with respect to time,
1/50th times.
it'll be dx dt, or 1/50th times dx dt. Because usually the derivative is just 1/50th, but then the derivative of x has to be multiplied. things in. I know theta. I know theta dt. And I'm looking for dx dt. So I'll put secant squared of pi over 6 times 60 pi equals 1/50th dx dt. I don't want to do secant squared. So, cosine of pi over 6, you know what cosine of pi over 6 is?
Right through.
Root 3 over 2. So cosine of pi over 6 is root 3 over 2. Which means that secant of pi over 6 is 2 over root 3. So secant squared will be 4/3. Because this tells me that secant of pi over 6 is 2 over root 3. So secant squared pi over 6 is 4 square top square bottom. Plug it in. Secant squared is 4/3. Reduce what you can. 3 and 60, that leaves you with 20 pi times 4. So 80 pi equals 1 over 50 dx dt. Multiply the 50 up. 4,000 pi. 4,000 pi feet per minute, since these were in per minute.
Where the radians cancel
We talked about this a little bit last time. We decided that
out? The arc length?
the arc length thing, really radians can be considered feet. There's a way to get from radians. You take a circle with a 1 foot radius, then however many radians you want to go is the same thing as if you went. So really, this could be considered feet here. Secant squared would be, this here would be actually feet per minute, right? Secant squared is a ratio of two things, so I think I'm pretty sure it's doing this. Right, see, all your trig functions are ratios, two things that both have feet. This guy here would be considered feet per minute. But this guy being a trig function is a ratio of feet over feet. So this would be units.